Alright, it is Monday. Welcome back from spring break. Hope you all studied binary analysis and vulnerabilities and exploitations because it is going to come in handy. So, homework 3, assignment 3 is released. You got a week and a day. Oh, 2 weeks and a day. So you each got it for a week. You're welcome. So the idea is you will all have access to a shared Linux server. I've already created all your accounts. Yegana will be emailing each of you with the account information and how to access it. That will happen after class, so I know you're not actually doing this during class. The idea is, and I can show you here, so when you have access, you will be on this system. It is living in my lab, so don't do anything bad on the network. I've actually blocked a lot of that stuff, but still don't do anything. Your goal is, if you run the score command, so there's a program in user local bin score. You can see that everyone here starts out at level 1. So your goal is to, well, each levels 1 through 10 are worth 10 points each out of 100. So you gotta get to level 10 if you want the points. Right now there's 15 levels. There will eventually be a total of 20, and the next ones will be really cool. Those are, going to be worth some points, but it's really more about getting on the scoreboard than it is about the points. So how does this work? So if I run the ID command, you can see that I am user ID, Adam D, group ID, Adam D. I'm also in group level 1. So if we actually look at I think it's group, you can see that we are all in group level 1. Right? So this is how your score is. You have to, so how do you get from level 1 to level 2? You have to hack something. So inside var challenge, you can actually, so you can read this directory. You can see all of the challenges here. So what are the permissions on the level 2 directory? Or sorry, the level 1 directory. So it's readable, writable, and executable by the challenge user. It's readable and executable by level 1 group. Who has level 1 group permissions? Everyone. Everyone right now, but me right now, because nobody has access to this. So inside here, you can see there's one file called level 1. So when we look at the permissions here, we see it's readable, writable, and executable by the challenge user. So challenge owns this. It is readable and executable with what bit set? The set group ID. So it's on the group ID. So the sticky bit set on the group, which is what this S means, so it's executable, and it will execute as whose group permissions? Level 2. Yes. And there's some file there, I have no idea what that means. So, can I access the level 2 directory? Why not? Because I'm in level 1, and we can see the permissions there, right? The permissions of level 2 is it's only readable or executable to people in the level 2 group. So your goal is, by using some kind of vulnerability in this program, you need to get access to the level 2 group and add yourself to its group. Luckily for you, we have created a handy program called Leap, where when you run this program, it will automatically add you to the next group level if you're one of the next group levels. So your goal for each of these challenges is to execute this Leap program as the next level of group user. So if I just did Leap, it'll tell me, what are you doing? You should be level 1 through level 16 right now to use this command. So if I'm able to execute this Leap program using the permissions of the 1 program, right? group 2 automatically. Questions on this? Yeah. So sometimes in this directory, let's see. So here, do you see any source code? No. So some levels have source code, some levels don't. Kind of depends, so you have to deal with that. Let's see. What was another important things here? Oh, there is something weird about, let's see, can I actually do it? Yeah, I actually don't think this will work because I don't know my password. It's not password, apparently. But I can go to my actual user. Yes. Okay, so ASL, I had to set up some tricks so that ASLR is enabled for the entire system. We haven't talked about exactly what that is yet. The important thing to note here, for level 8, there's 8, and then there's 8_real. There's several levels like this. The 8_real is the program you should analyze. This is something that has the vulnerability. 8 is just a wrapper that calls 8_real, but it disables ASLR when it calls that. So you're free to analyze it. It should be a super tiny program here, but this one is set UID as level 8. So if you just try to execute 8_real, will that do anything? So if you break this 8_real program, what permissions do you have? Level 8. And you already are level 8 to even access this directory. Right? So you want to run the 8 program. Cool. Any questions? This is really fun. You should look more excited. This will be the best hungry time you've ever had in your life. So what do you turn in? So what you're going to do is turn in all of the source code that you've written for this assignment. So if you wrote any C code or helper functions or Python code, whatever you write to solve this, submit that. Also a README that specifies exactly how you solve each level, so all the commands that you're running on there. I guess I don't really want to tell the story, but please no funny business, right? So there's a couple things. A, remember you're on a shared system. Right? So everyone's going to be using this. I've put in some things so you can't fork bomb somebody else, but try not to let it happen because it sucks for everyone when the system's down, and then one of us has to go in and try to fix it. So don't do that. Also, be careful of what files you're leaving where. Right? If you leave your exploit in some temp directory that's world readable, and somebody else grabs that and submits that, we see, we have 2 people who submitted the same exploit at the same level. This is like a potential academic integrity violation problem. Right? So don't put us in that situation. Make sure you're responsible for all of your code and your exploits, right? So somebody submitting your stuff is the same as if you give it to them, whether they stole it from you or not. Let's see. If you get, on a happy note, if you are able to get root on this system by exploiting some vulnerability somewhere, let me know. I will give you extra credit points, but don't use that to ruin the fun for everyone else. Just to know what you're doing. I had one person say, hey, I can do ls/, and that's like the root directory, so I become root. It's like, no, I want to see that your user ID is root on this system, right? Let's see. We didn't do it yet, but say at a high level, just like some of the checksum stuff for the other assignment, right? These are basically like puzzles. Right? Each level is like a puzzle, and it's very easy to share your solution with somebody as the solution to a puzzle that they can just run and do. Don't do that. It sucks for everyone. If you're struggling, come to office hours. So you should start this now so you can get help. Because we'll gladly help you as much as we can in our office hours. We can have more office hours. We want to help you. We don't want you to be stuck. I mean, you need to be stuck somewhat, right? You need to be able to think your way out of problems. But getting stuff from somebody else just sucks because you're ruining all of your learning, right? You're not actually learning anything. So that's very cool. Don't do that. Also, don't try to scam answers from anyone else. Can't believe I have to say this, but it has happened in the past, and that student got expelled, so don't do it. Good? Alright, happy stuff. And, okay, yeah, final note, so start early. So this is definitely one that if you try to do this the day before it's due, you're going to run into some problems because you'll be analyzing code, you'll be trying to understand how the binaries work, and you really need time in order to process these things. You need time to get stuck and to think about what it is that you're stuck on so you can think of ways around it. That's where you get a lot of good security knowledge so you can really find ways to break this stuff. Yes?
Yeah, assignment due date is different in important dates and the one which is shown.
Try refreshing. I updated it at some point.
I did that, but it still shows me 28th of March.
It should be the 28th. Is that what I said?
Because the page which you just opened, it says 27th. Okay.
Wow.
I already updated it. I guess I just had an old version of it. Yeah, so a week and a day. It should be like Tuesday.
Yeah, and how do we get to know how much marks we got for assignment 1 and 2?
We're still grading assignment 2, so once we're done grading assignment 2, we'll email you with all the correct, individually we will email you with your current grades in the class. So. Anything else? Class stuff. Alright. On to buffer overflows. We're back to buffer overflows. So, what is the core problem? Yes?
Sorry, what's the syllabus for midterm?
Everything up to the date before the midterm. Everything up till some month, Wednesday. So, we looked, to refresh your memory, we looked at a timing program like this to see what happens when we try to copy a string onto a buffer that's allocated on the stack, where that string is larger than the buffer space that is allocated. So we're not going to go all the way through this. So what's the core problem there? Why? What is the fundamental problem of these buffer overflows?
There's nothing limiting the stack's movement, or limiting your stack and movement, or the movement of the pointer on the stack.
Whose pointer? What pointer?
The register that points to the where you're writing on the stack.
Yes. Okay, so arrays fundamentally in C, right, are just pointers to memory. And array access operations are just offsets of that pointer. So there's nothing in there that is checking that, hey, am I writing to allocated memory? Right? So fundamentally, all buffer overflows, and they really fall under this general class of memory corruption vulnerability, is you're able to write to memory that is outside of where you should be able to write. And so there's a class of functions that are all inherently unsafe. So whenever you see the use of one of these functions, you should immediately start thinking buffer overflows or some kind of memory corruption vulnerability. These are the gets program, the gets function. So what does this do? Anybody use this?
Takes a string from the user.
What's that?
Takes a string input from the user.
More specific than from the user. More specific. Standard in, yes. It doesn't have to come from the user. It doesn't have to come from the console, right? It's standard in. So we know it's reading from standard in. And gets is incredibly unsafe because if you look at the man page, it says you pass in a buffer to gets, and it says, well, it reads in from standard in until it gets to either a new line or an end of file, and it adds that to, it appends that to the buffer. So there is fundamentally no way for the programmer to specify the maximum size that should be written to this buffer using gets. So gets is inherently unsafe. Other functions, string copy and string cat, these are other functions where, as we saw the string copy before, right, there's nothing that says how many characters or tries to limit how many characters should be written into the other buffer. S printf, so what's the difference between sprintf and printf? What does the S stand for? Secure?
Safe.
What was it?
Safe.
Not safe? String. So instead of printf automatically prints out to standard out, fprintf prints out to a file, sprintf prints out to a string. That's what the S is for. So to print out to a string, you need to pass in what as a parameter? You need a format string, but you also need a buffer. You need somewhere to write this result of this format string into. So actually this is good. Let's look at this. Actually, let's do it on the Linux box. Always good to go to documentation. So we have get s is passed in a character string, and so we can see reads the line from standard in into the buffer pointed to by s until either a terminating new line or end of file, which it replaces with a null byte. It says no check for buffer overrun is performed. And see bugs for more information instead of never ever use this function. I don't know why it's still in the standard library. This is where you should get all your information about functions. This is the gold standard for information. And trust me, 9 times out of 10, when you put in fgets or string copy into Google, what you're going to find is a web page that is the man page of this. But you just cost yourself 30 seconds and a round trip to Google, when you could just go on your terminal and type it right there. So I'm trying to save you time. So string copy, we look at the signature has a destination and a source. And so if you read this, it says the string copy function copies the string pointed to by source, including the terminating null byte, to the buffer pointed to by dest. The string may not overlap. That would be a weird problem. And the destination string must be large enough to receive the copy. Beware of buffer overruns. At least this is in all underscore and like exclamation point, right? So at least say that you should be aware of this. So we had sprintf. So we can see, look at the sprintf. So here we have a character pointer to a buffer, then we have the format string. And then we have, what is the dot 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 here? There's what?
Variable number of arguments.
Yeah, variable number of arguments depending on the format string itself, right? So format, all of the printf family of functions are all of this style where you can pass an arbitrary, essentially, number of arguments to it. Let's see, sprintf, write to the character string. So we can actually see there's 4 here. And we have the scanf family of functions. So scanf reads in a format, and then, let's see, I think it's what, %s is how you read in. Yeah, so this is given an array p. What? Say it again? Oh, okay. I was probably getting the wrong one. So scanf, scanf, and fscanf are all other types of ways that you can overrun. These are just kind of the classic. These are the library functions that are inherently vulnerable. So if an attacker can control the source buffer, right, because we know, and if the program has allocated a static buffer for the destination, we know we can always provide input that is larger than that fixed buffer, right? So we can always try to get that to overflow. But we have to be aware, right? You can still have a buffer overflow in a custom input string, right? Somebody can call getC, which getC returns what? A character, 1 character. So it's getC, returns 1 character, right? They could write a custom read routine that reads until the end of the line and doesn't do any bounds checking. Or they could do bounds checking, but maybe they're off by 1, right? And so you have to analyze these custom input routines too. Your first check should be for like these 4. If you see any of these, you should immediately start investigating further. If you don't, then you need to maybe look for other ways that this could happen. Okay, so we've looked at a high level what a buffer overflow is. We can overwrite a buffer. Specifically, we've looked at if we can overflow a buffer on the stack, what are the important things on the stack that we want to try to control?
The pointer.
Which ones?
The call when you function. So you can return. You can go to an arbitrary.
Yeah, what is it called? Saved instruction pointer? Yes. So saved instruction pointer is going to be our main target. So that is the instruction pointer that is saved on the stack, that when the function returns, it will jump and start executing code there. So, as how to actually exploit this, because we've only been talking about this at a very high level, right? We've been talking about it as, hey, here's what a buffer overflow is, and I'm trying to convince you that, hey, if we can control this saved instruction pointer, we can start executing code, but how to actually put all those pieces together. And how to actually exploit this varies based on the exact assembly, the operating system calls, alignment. There's a great paper that I highly suggest you read called Smashing the Stack for Fun and Profit. And when I say paper, I mean it was published in like a hacker magazine. So it's not really like a paper. It's more of like, hey, here's this cool thing I found, and here's how you can use it to exploit buffer overflows. And it's always helpful to actually go back to this original source to try to understand what's going on. But fundamentally, so let's say we can use a buffer overflow to control this saved instruction pointer, then what do we want to do? Uh-oh. Let's pause. Wait, let me see. Slideshow. Okay, now we're good. Got rid of the presented run. Okay. So, we can overwrite the saved instruction pointer. Fundamentally, what does that mean? So we can control that instruction pointer. What does that actually mean? Yes?
We want to jump to a function that we control.
We want to, so with that saved instruction pointer, if we can overwrite and put arbitrary values there.
We want to jump to a code that we can exploit the program.
Yes, but now we need to actually run code of our choosing, right? We want to execute some code that we chose, right? That performs some computation that we want to. And so to do this, the kind of general name for this is called shellcode. So with shellcode, the goal is we want to execute arbitrary code in the vulnerable applications process space. Remember, right? Because we're trying to exploit some other application that's running. It's running its own process, its own memory space. We can't access that memory, otherwise we can just own it completely, right? And so we want to be able to execute some code in that vulnerable apps process space. The key is that this code has the same privileges as the application. So if it's a setuid root application, now that code that we're executing is executing with root permissions. Similarly, for the homework assignment, when you execute code and that calls the lead program, it looks up and it says, hey, it looks like you're in the next group. Great, I'm going to add you to that group. So shellcode is the standard term. Shellcode is the standard term for this type of code, and it's called shellcode because the classic example of what you want this to do is to execute bin/sh, which executes a new shell, which now when you type in commands to that shell, you're running those commands as the owner of that application. So from there, it allows you to execute everything, but fundamentally, there's nothing that says shellcode only has to call bin/sh. Right? You can write custom shellcode to, let's say, called, I can't remember what it's in, like user local bin leaked. You could do that. Or you could write shellcode to, I don't know, delete all their files or something without ever calling bin/sh. You can do some really cool stuff. It's really just assembly code to perform a specific purpose. That's really the way to think about it. Rather than like, oh, it has to spawn a shell to be like shell code. No, it's just a chunk of assembly code. So if we want to do just a bin bash shellcode, we can first, and the way to do this when you develop shellcode, you want to first write what you want to do in C, because who wants to write x86 assembly raw? I mean, it is kind of fun, so you have to write some of it by hand. But to really understand what's going on, we'll look at a C version, and we'll see how that compiles down, so then we can understand how to write the assembly code by hand. So we have an array, a character pointer, right? So we have an array of character pointers. Name 0 is going to be the string /bin/sh. Name 1 is going to be null. And we're going to call execve, passing in name 0, name, and null. And then we're going to call exit. So what's the execve? What is that? What's the function signature for that?
Does it fork a new process and try to execute whatever string we give it?
Nope. It was going to fork any process before, yeah.
The binary name and then a variable number of arguments.
Yes. So important that we go look at this up. Very good. We're recording now. So, important thing. First, let's see. How can we tell here? Oh, sorry. Okay. First thing is execve is a system call. So it's a call from the user space to the kernel. The exact arguments are, can you all read this in the back? Good, okay. So, execve takes in a file name, an argv array, and an environment pointer array. And it says it executes the program pointed to by file name. File name must be either a binary executable or a script starting with the lines of the form, the hash bang, and the interpreter, which you probably dealt with in homework 2. argv is an array of argument strings passed to the new program. By convention, the first of these strings should contain the file name associated with the file being executed. Environment pointer is an array of strings conventionally in the form key value, which are passed as environment to the new program. Both argv and environment p must be terminated by a null pointer. And so the argument vector environment can be accessed by the called to program's main function when it is defined like this. So this is exactly how, when you write a C program, how your arguments are getting passed into this program. Right? So we looked at bash and we saw that bash calls fork. We know it calls fork because it's creating a separate child process. And then it's calling execve with the name of the program you want to execute and your argv vector and the environment. So when we want to execute a new shell, other important things, execve does not return on success because it completely overwrites the current process, and the current process is memory, right? So it completely changes it. There's no returning from this, right? It literally becomes a different program. Let's see. The text, data, BSS, and stack are overwritten by the program being loaded. Cool. All right. So what is this call going to do? Yeah.
Call bin sh with no environment.
Call bin sh with no environment. What arguments is it passing to bin sh? What's the argc going to be when bin sh is called, is executed? 1, and then what's argv 0? String bin sh, and argv 1 should be what? Null. Perfect. And no environment. So we're executing bin sh with no environment. Why do we have this exit 0? Because we're nice people. We don't want things to just like, what if it fails? Right? If there's any problem, we exit cleanly with a 0. So, if execve was a library function with cdecal calling parameters, then how would we call execve? What would we first do to call that? Like, what would the assembly instructions be? It's the first thing we have to do when we call a function. Push the arguments in what order?
Right to left.
Right to left. So we first push null, then we would push what? The address of name. And then we would push the address of name 0. And then we would call execve. And then it would execute and it would never return. Unfortunately, it's not a library call, it is a system call. So the calling convention is different. So we have to keep that in mind when we handwrite this assembly. So we are calling into, so the parameters are actually usually in registers. There's a fixed number of registers, and then if you are passing more parameters than registers, then you push them onto the stack. And then you call, you create a software interrupt, and you pass the hex value 80. So to call execve, first you need to tell the operating system which system call do you want to call, right? Because you're sending a signal to the operating system, you're passing 80, hex 80 as that signal, which means that the operating system goes, okay, you're calling a system call, but which system call? There's actually a huge number of them. So to do this, you put the value hex B into EAX. So the EAX register has the index of which system call you actually want to call. And these are all defined, I think it's called syscall.h. We'll maybe look at it in a second. But these are all defined somewhere. Then we put in EBX, we're going to put the file name. So the address of so a pointer to the string /bin/sh will be in EBX. Then the address of what we saw as the name variable, right? So an address to a 2-array address, where the first one points to the string bin/sh, goes in ECX, and then null, well, we can put null in EDX, and that'll be fine there. And then we want to call int 80. And that will trigger an interrupt. We'll go to the operating system. The operating system will see, oh, you call the system call, you call the execve, let me pull out all these parameters. Great, I'll execute this program for you. Similarly, so we have the exit. So exit is actually also a system call. So exit, the index is 1, so we put 1 in the EAX register. We put the exit code that we want in EBX register, and then we call int 80. So that's what that'll look like. So it's important to look at this when we look at the actual assembly code that the C program generates to see what it does. Okay. Let's think about what we need for this. I need to. Alright, I lost a USB connector. Alright. Cool. Okay. So let's think about what we need. So, for execve, right, we need hex B needs to be in register EAX. We need an SH here. And then we basically need an array with bin sh, and then null, and we need to pass in null. So this is what our goal is trying to execute here. So we want to craft some code to do this. So to do this, we need to somehow move b into EAX. And then what needs to be in EBX? The address of what? Bin sh. What do we also then need?
Some memory containing bin sh.
Yeah, we need bin sh somewhere, right? We need literally the bytes /bin/sh somewhere in the program. So, let's draw kind of over here. We need the string /bin/sh somewhere in memory. Let's call it memory location, we'll call it alpha. Right, so at memory location alpha, the first byte is slash, alpha plus 1 is b, alpha plus 3, like 2 is I, plus 3 is n, then /sh. And we can't forget the null terminating 0 at the end here, right? If there's no 0 there, then we don't have the right thing. So, we essentially need alpha to go into EBX. Then what do we want to go? Can we put alpha into ECX? Why or why not?
If it's contiguous memory space, you could. But if you're just allocating, you need a pointer to that string. So if they're right next to each other, you can do that. But no.
If they're right next to each other? So what circumstance could I do this? So how do I change this memory layout to make this work?
If two contiguous strings, you put pointers, one points to that string, and somewhere else in memory, one points to, well, one is just.
So what I need, exactly, so what I need is a memory location, right? This is alpha, and this is null, right? It needs to be a null terminated array. But can this live at alpha? What would that mean?
Oh, the overflow over the null pointer right up above the alpha.
Yeah, alpha can't contain, the first 4 bytes of alpha are /bin, right? So these are the first 4 bytes. So unless you got weirdly lucky and put this string at the memory location /bin, it's not gonna work, right? So we need somewhere else. So we need some kind of a beta, right? And we need beta to have, when you dereference beta, it has alpha. And when you dereference that, it points to the string bin/sh. And then beta plus 4 better have the value null there. Because remember, when we looked at the function signatures, right, so we go back here, the argv is a pointer, right? So beta here is a pointer. When you dereference that, you get another pointer, alpha. When you dereference that, you get a character, and you get that string. So we can't put alpha into ECX. We need to put some, that's not very good. You need to put some other address beta where the first entry there has alpha and 4 bytes above that has 0, null. And then what do we want to put in EDX? 0, null. So I'm writing null here just to be very clear, but it's 0, right? We want the zeros there. Okay. So it's kind of tricky, right? What's tricky about this? Or does it look super easy? You guys ready to do this on your own? What's the difficult part?
Determining what alpha they are.
Go ahead.
Determining what alpha and beta are.
Yeah, determining what alpha and beta are. So, is it, we're already assuming what about the program? assuming that we can write into its memory, right? That's the nature of the buffer overflow, right? We're going to use the buffer overflow to overflow a saved instruction pointer, right? So can we put into what we're overflowing the string /bin/sh? Maybe. I mean, it depends. So we can maybe get that string in there, but yeah, then the tricky things are how do we define alpha and how do we define beta? So keep that in mind as we continue. So we need the null, we were talking about this, we need the null terminated string /bin/sh somewhere in memory. We needed the address of the string bin/sh somewhere in memory, followed by the null pointer. So this was beta in our example, right? We needed alpha followed by null. And we need we need null somewhere for environment pointer. So our goal is going to be copy B into EAX register, copy the address of the string /bin/sh into the EDX register, copy the address of bin/sh into ECX, copy the address of the null word into EDX, execute int 80, and then copy 1 into the EAX register, copy 0 into EDX, and then execute int 80 again. So what are these last three doing? Exit. Just calling exit. Just to be nice. So if we were to write this in assembly, we would have a data segment, we'd give it a label, we'd call it sh, we'd have the string /bin/sh, we'd have an integer 0, and then our program is pretty straightforward, right? We want to just translate exactly what we wanted to do into assembly. So we can set b to be hex b, which is the same as 11, right? 10 is A, B is 11. We can then move SH into EBX. So this, we'll use this, and we'll see how this compiles. So this will move the address of this string /bin/sh into EBX. We then need to do what? So this is alpha, so we've set up alpha, but what do we now need? We need beta, right? We need something that has 0 and then alpha, and we need to get that address. So what can we use that has space for temporary variables? The stack. So we can create this chunk, this beta that we need on the stack. So we can first push null, which will push 4 bytes of nothing. Then we can push this actually EBX onto the stack because that will be the value there. And then we can we can query the stack pointer to figure out where we are in memory, and that will be our beta. So we've solved the beta problem. We don't need to worry about beta because we can just use the stack. We'll push 0, we'll push SH, then we'll move the stack pointer into ECX. Right? So we think about it exactly at this moment. Not as good, but I can try drawing it. So we think about what the stack looks like. So we have bin sh somewhere at, let's call it address of sh, right? So the stack, right, pointing somewhere here. Do we know anything about what was above the stack? Nope, we don't know. But we know that it's used by the program, right? Although we don't really care because we've just taken it over. So the first thing we're going to do is push 0 onto the stack. So this whole thing is going to be null. Then what's the next thing we push onto the stack? The address of sh. And then we have stack pointer, I don't know how to do this, so. ESP is pointing here. So, right? So now this, wherever ESP is our beta. So now we have beta, which has alpha followed by null, and alpha has the string /bin/sh. So we move that into ECX. Finally, we move 0 into EDX. So we set up the environment pointer just to be null. We call int 80. And we're good. And then we can clean up. move 1 into EAX, move 0 into EDX, and then call int 80. So we can I just try ending it and doing it again? See if this works. There we go. Perfect. Okay. So we can compile this. So we can write it in a .s program. We compile it for 32-bit. And then we can run it because GCC is going to turn it into an a.out file, an executable binary. We can run it. And what are we expecting it to do? If this works, what do we want to see? A shell. Yes, we want to see a new shell. And just as if we called /bin/sh. So bin/sh is like the super primitive version of bash. So it shouldn't have any of this fancy host name stuff here. So when we do that, it looks just like this on one system that I ran this on, sh-41.$. So that's how we know it works. It actually successfully called exec.
And can we execute arbitrary commands from that command line?
Yep. At that point, we can type in anything. We have ls id. Now here, we ran our own program, right? This program is not running as any different user, right? It's running just as us. But fundamentally, we could write it, change it to do whatever we want it to. I mean, it could run any program that we want. And we can even change, you can change this shellcode to do anything you want. Rather than calling exec.de, bin/sh, you could call /rm/rf, /bin/rm /rf. You could set that up to just wipe all their files. And it would just do it, right? You won't see a shell prompt, but it's still doing what you want it to do. This is just a nice way, because as a human, it gives you a nice way to kind of use the tools you're familiar with to interrogate the system. So, we can take this file, we can compile it into an object file with the -o, or sorry, not to an object file, to an executable. And then we can use object dump on this to look at what exact assembly code did the compiler generate for this, right? What did it look like? So let's look at it. So the main function, we can see move b into EAX, move, what's this value into EDX? Yeah, so that is the address of sh, right? So the compiler created probably a .data segment and put the string /bin/sh in the executable and told the program to load it at this memory location when it gets executed. Then push 0, then push 804.961C, move the stack pointer to ECX, move 0 to EDX, int 80, move 1 to EAX, 0 to EDX, and call int 80 again. So, now we need to test our shellcode, right? So we tested it a little bit by running it, right? So that shows us that yes, it does, it should do what it's supposed to do, right? But we're just running this as a program when really, when we execute this, we're going to inject this code somewhere in their application's process space and it needs to be executed. So we can actually simulate that with the C file because C is a terribly unsafe, horrible language. So you can do this. You can create a variable called shellcode. You can copy these bytes. Where did I get these bytes? From object dump. So these bytes right here. The third column here, or the second column, shows all the bytes of these instructions. Right? So B8-0B-0000000, BB1C96. Look at the next one, B8-0B-0000000, BB1C96, and so on and so forth, right? So those are just those bytes copied over. And then we're creating, what's this doing? Thought you knew C, huh? So you read something like this. What is it?
Function to a, or it's a pointer to a function.
Yes, it's a function pointer. It's a pointer to a function that takes in 0 arguments and returns an integer. So we can set shell, the function pointer, equal to shellcode, and then we can call shell, which will start executing this program. Now, We have to actually add some compiler flags because, as I told you, there's been a lot of defenses built up over the years against buffer overflows and these type of vulnerabilities. We'll see when we get to advanced techniques of how to bypass those. But in order to do that yourself, you need to compile it with special flags. So this, because right now, this character shellcode, this is going to be on the stack, right? So we need to tell GCC to make the stack executable. So that's what this flag does. Then if we do this, yeah.
Does that still require that bin sh is in on the stack somewhere in memory space somewhere in the application?
Yes. So what? So when I execute this, what was the success on the last one? Oh, we got a shell. Are we gonna get a shell this time? Why not?
Doesn't know what bin sh is.
Yeah, it's gonna say, it's gonna give me nothing, right? And if we look at this, what's the problem with this assembly code?
You don't own that address.
Yeah, there's no /bin/sh at that address, right? At 804.961C, who knows what's there, right? And why is that? Why don't we know what's there? Yeah.
We don't know the memory for that region. We
Yeah.
have to know about finding ways.
All we control is this shellcode, right? As far as right now, we just took this shellcode, and just like in a buffer overflow, we're going to inject it into somebody else's process and get them to start executing it. That is exactly what this code does right here. Right? This code, all this C code does is, hey, here's a string, I'm going to execute it. That is exactly what our buffer overflow is going to do. But our shellcode that we wrote assumed that there would be the bytes /bin/sh0 located at memory location 804.961C, which does not hold for this other memory location. Yeah.
Can't we write some kind of code that finds the address where that is?
Well, what if it doesn't exist? Who says, why does the string /bin/sh have to be anywhere in their memory space?
Well, then if it doesn't exist, create it, right?
Yes.
We modify our shellcode to push it on this thing first.
Yes. So, always go back to your tricks. That's like one of the key things you should learn. If you learn little tricks, like we learned getting around beta to have to know the address of beta, right? Well, use the stack. The stack will tell you the address. Here the problem is essentially alpha, right? There's two problems. A, we know the address of alpha, but the problem is we've hard-coded it, and we don't know we can't guarantee that the string /bin/sh is going to be at that address. So let's get around that, let's just use the stack. And the key problem is we need position-independent shellcode, right? We need shellcode that can execute in any process and call exec_de without worrying, oh, is there the string /bin/sh at this fixed memory location, right? So if you think about it, the problem was the code that we wrote was fixed to this one location when we need to write new shellcode that can be executed in any process's space, regardless of what's there. So we can do that. It's really cool. So we'll again move 11 into EAX. Now we'll exactly use the stack. So we'll push 0, so /sh0, and then we'll push bin on the stack of /bin/sh0. Right? We have to be careful about endianness here when we push this onto the stack. So we think about, again, we always want to think about what's the stack going to look like.
Can we see the stack to see if we're...
In what sense? Yeah, draw it with your hands.
No way.
I'm not joking, I'm not being facetious. I do this all the time now, and it helps me so much on these things. I will literally draw the stack, I'll draw what the variables are, I'll draw like where the offsets are, GDP, and then everything becomes so simple. It's like, oh yeah, this is 90 bytes down from EVP, that means I need 90 bytes of this, and then I know there's saved EVP of that, so I'll do that, and then this, and then you can write shell code in like one go. Also, when doing this, like I will draw, just like I do here in class, like this isn't stuff I just do for fun, I do it because it helps me think about these things.
Can we print the addresses to see if we put the right stuff at the right?
Yeah, so you just have to debug this. You have to debug this code, and you can step through instruction by instruction in GED and look at what the stack looks like at these locations. So, when we get here, right, we have ESP. Again, just like before, there is something above us on the stack, but we don't necessarily know what it is. Then, we're going to push, essentially, it's in reverse, but it's going to be /sh and then 0, the character 0. Alright, so this is a null terminated string here. Right? And then we're going to push /bin. So it'll be /bin it'll be /sh0. That's how this all works. So this is now the stack looks here. Now we need to get alpha, right? Because so now we've done our first step. We've put the string /bin/sh0 somewhere into the process's memory. And it's somewhere right here that we can get the pointer to it, right? We know that ESP points to what we want as alpha right now, right? And so we can just copy ESP and put it into EVP. That's where we want alpha to go. So this here now is this is alpha. We will then push 0. We'll then push EVX. I'll be even better at this and all the shortcuts now. What's in EVX right now? Alpha. So now ESP points here. And then what? Yeah. Now this becomes beta. Right? And now we set it up so we have in EAX is the value XB11. In EAX is a pointer, is the memory address of the string /bin/sh0. And in ECX is the pointer to an array of the first one pointing to a string that is bin/sh, and the second one being null. And then we have 0 in the environment pointer, so then we call int e. And we have our cleanup. So now we can execute this, and this will work. So we want to do our first thing, right? We want to compile it just to make sure this works. If it doesn't work in its own process space, it's never going to work in somebody else's. So we can compile it like this. We can look at the object dump. This is an important thing to do, right? So we can see, look at this. We can take all these bytes, copy it into our shellcode tester. We can execute it or compile it with an executable stack, run it, and we'll see that we actually get a shell from here. Right? So now we can take this code, as long as we can get somebody to execute these bytes, right? In their process space, it will spawn a shell. Questions on this? Yeah.
Sorry if this is a dumb question, but do we absolutely need that part at the end where we're doing an exit 0?
Nope. It's just a weird convention. But no. So what's the benefit of smaller shellcode?
You don't need large of a buffer, so you don't have to worry about running with something that you don't know and crashing the program.
Yeah, so you may, it all depends on the program, right? But let's say you can only get, like, let's say it's Twitter, you can only get 140 bytes into the program. right? And maybe that's enough for an overflow, but it's maybe not enough for an overflow plus shellcode if your shellcode is really long, right? So there's a couple ways around that. So yeah, there's all kinds of tricks of how to make your shellcode as small as possible. There's also, you can also do crazy things of have your shellcode in stages. So you first have a really tiny shellcode that then connects back to you and reads more bytes. So then you send more bytes that it puts somewhere else and then executes. So you have a stage 1 and a stage 2 shellcode. All kinds of crazy stuff that you can do with shellcode. You can even, so we'll talk about, okay, so now this leads us to another important thing. So it was not a stupid question, it's a very good question. So, when programs, so let's say you have the string copy function, right? So string copy copies from one buffer into another buffer. We control the source buffer, right? When does it stop copying? When it reaches a null byte. So when would it stop copying if we wanted to use that to include our shellcode into their process?
The first 2 bytes. Only copy the first 2 bytes.
Yeah, literally it would only copy the first 2 bytes. It would copy B8, 0B, and then the null byte. So technically 3 bytes, right? So that's one problem. The gets routine, we said stops on what? It stops at end of file or what? A new line, yeah. So I actually don't know, is there any new lines in here? But this is actually part of the challenge, right? This is probably something you've never thought about before. You've only written code and then ran it, right? Or compiled it, interpreted it, whatever. Here we need to write, not only write assembly code by hand, but now we care about what bytes does that assembly code correspond to, right? Our goal now is, can we write the assembly code that does exactly the same thing, but has no null bytes in this program? And no new lines. So those are the 2 things we want to avoid. So, the way we do this is we look at this offending code and we see, okay, which instructions in here are problematic? The push because of why? Because we put a null pointer, we put a 0 in there, right? We wanted to include the null pointer in /bin/sh null, right? We have to have a null byte after the string /bin/sh. But what else can we do? Yeah.
Append it later.
And we can append it later. We can, if we're pushing this onto the stack, we can push 4 null bytes, just like we did on that 6A00, the push 0, right? That pushes 4 null bytes onto the stack. And then if we push, well, bin/sh, then at least at that point it will be null terminated. So that's one issue. What about that? What about the first one? What's the problem there? What are we trying to do with that very first line? What was it?
Is it copy?
Yeah, what is this doing? Why are we doing this?
We're copying a value of that register.
Why? Yeah, it's a system call. So we have to, so in order for, so you always want to separate and think about, what are we doing that we have to do? And do we have to do it this way? So that actually goes back to the question about the exit, right? Like, I wouldn't even worry about this at this point. I would just get rid of it, right? And say, like, screw it, we don't need it, right? A bunch of zeros, I don't want to think about how to get rid of this. So by the time, the thing that we must have happen, right, is that by the time we get here to this int 80, there better be the value of 11 inside the EAX register. You agree? Do we have to get it there by moving 11 into EAX? What else could we do?
Write like a bunch of FFFs and then subtract FFF minus 11.
Yeah, so we can move all Fs, so we can move, I think it'd be 1, 2, 3, 4, so 4 Fs here into the EAX register. or no, maybe 3? No, 11, yeah. So it'd be 4, wait, no, FF, yeah, 4 FFs. So we could move that into the EAX register, and then, so that would be -1, and then we could either, well, you could add from there, you can do, I think there's an increment operator, so you can increment from there up until 11, so you can have 12 increments. What else can we do? What?
A combination of shift and increment.
So we could speed up, because having 12 increments in a row is kind of silly, right? So we could do maybe a shift left, so each shift left is basically ×2, right? So we could have a shift left by however many we needed, and then an increment to get the values in there. Why is this instruction 5 bytes?
It's moving a 32-bit integer.
It's moving a 32-bit integer into EAX. What do we really need to be in there?
8-bit.
We just need 11, which is only really 1 byte that we care about. Right? Yeah.
So we move 11 to like EAL, the lower.
Yeah, so no L, just AL. So the AL. So if we moved 11 into AL, it will then, so you have to experiment with this, right? You have to see, will the instruction actually be smaller like I think? The answer is yes, it will only be 2 bytes, but will that actually work in any single process? Yeah.
What if you had extra stuff on the top?
Exactly. What if we have extra stuff? So the problem with shellcode is we have absolutely no idea about any of the registers or any of the memory, right? Fundamentally, we can't make any assumptions that, oh yeah, everything else is just 0. So how do we zero out a register? Because we move 0 into it, right? But that doesn't work very well, because then we get null bytes. So we can XOR that register with itself, and there, no matter what bytes are in there or bits are in there, we know that the register will be empty by the time we're done. So that gets us out of here. So this will do with a combination of XOR and basically a move. Move B into AL. This will get rid of by pushing. So and then you can actually start being very clever about reusing things, right? And you can kind of get in too much of a trap if you, because this is pretty straightforward code that you can easily kind of change around. But once you, let's say, like you can XOR EAX, so now you know EAX is 0, then you can push EAX onto the stack to get a null byte, and then you can push, and then you can move B into EAL. But maybe you want to use EAX later, so maybe you use that later. Like, I don't know, there's all kinds of ways you can go about doing this. And the more convoluted and, have you guys gotten to this where you're trying to like write assembly and minimize the like number of instructions and the number of registers, and like, you can kind of go crazy, and at the end you have something that you have no idea what anything does, and everything's all interconnected in this big ball. So, we can XOR EAX with EAX. It turns out this has no null bytes in it, so that's good. We can push EAX then onto the stack. But now when we want to push the string, what string do we want to push? It's not a trick question. /bin/sh, right? How many bytes is that? 7 characters that we want to push onto the stack because we no longer have to push the remaining null byte. But how many bytes does the push instruction push onto the stack? 4. But we have 7 bytes. So how do we do that? Add a space. So yeah, we kind of need the file system equivalent of a space, if you will, right? We need an additional character that doesn't actually change which file we open, right? But that gets us to that nice offset, because otherwise, I guess we could do it. We could do a space first. So the first character could be a space and then /bin/sh. But then to get that address of alpha, we'd have to subtract 1 from it, so it would be an offset of where it actually was. It would be a huge pain to actually do that. Does anybody know a character that doesn't actually affect what file you open? Yeah.
You did bin and then 2 slashes?
Yes. So file systems are super weird. I don't actually know exactly where this behavior comes from, but if we do /bin/sh, that works. Or /bin//sh. You can actually have as many slashes as you want, and it doesn't change which file you open. So we're going to do //bi and then n/sh, and then the 0 comes from the previous push of EAX. So there's 4 bytes of zeros, then there's //bins, bi, and then n/sh, and then zeros. Then, now at this point, we have our alpha. So those that have any problems will move alpha into EDX. Yeah?
If you put a space after SH, will that be a problem?
No, yes, that will be a problem. It will try to exec a file. You can have spaces in file names, right? You just have to use quotes when you access them. So, yeah, that would not access the right file. Push EAX, push EBX. So why are we pushing EAX here? Null byte, right? We want to push another null, right? We need to have null and then alpha, and then have that be our beta. And so we're reusing this EAX register, the fact that we know that EAX has 0 in it. Then we push EBX, so that we push alpha onto the stack. And now we move that stack pointer to ECX. Then we move EAX into EDX, and now what is EDX's value? 0. So I don't know if I just did this because I like this. You can also try, is it less bytes doing this versus XOR EDX with EDX? Because that would have the same effect, right? So it's kind of fun, you get to experiment. And then we move 11 into AL, and then we call in 80. And we can also do the same thing here if we wanted to, but we don't have to really do that. And if we compile it, we'll see that it actually works. We can test this. We can see that it works, except that this actually doesn't work, so you'll have to actually do this on your own. These bytes aren't correct, so you'll have to actually compile this and create your own shell code or maybe not, I don't know, depending on what the challenge is about. Cool, all right, I think that's good. We got here, and then we'll put it all together on Wednesday. Full overflows, shell code,